No, Thabu, it's still not doing it right. It's not it's pointing at somewhere where my pen is not there. Yeah, please. Okay. So we have seen about vector spaces, we have seen about linear transformations, we have seen examples of vector spaces, examples of linear transformations. What we would be doing today is we would be looking into a notion of a subspace, and just to make the setting right before Thabu comes and helps me with this. So we have sets, and then we have subsets. Okay. In parallel, we have vector spaces, and what are subsets to a set is the same thing as a subspace to a vector space. Okay? So, remember I said that if you have a vector space, it means that it is a set along with. So vectors, the whole notion of a vector space comes encapsulated with the notion of this binary operation of vector addition and the scalar multiplication. Okay? Now let's see. What is a subset? Well, subset is just as you had a big bag, you take a few from there. Right? So we expect a subspace to be so we take some of the vectors, right, from that bigger space. But that must be a vector space in itself. Okay? Right? If you start thinking of the analogy, if I take just something from a set, it makes a set by itself. Okay? Being a subset is something more, but first, its first identity is that it is a set by itself. So similarly, if I take some of the vectors, I should do it in such a way that they still make a vector space. Okay? By itself. So, there must be a very natural way to say how to add two vectors from those small given subcollection, right? How do I scalar multiply them? And there must be this zero. Now, and inverse so negative vector and so on, right? So, as I say, and I go on saying this, every time, mathematics is a very, very simple subject. Okay? You do the simplest thing that is possible. So, the only information you have, if you just think, the only information that you have at your hand is the vector space that was given to you. Right? Nothing else. And I have now given you some vectors from this vector space, so that it should make a subspace. Okay? So I'm saying this new collection, sub-collection that I have given to you should make a subspace. What should be the zero? Well, there was this zero already there in the parent space. Okay?
Oh, you know what? Sometimes when you put this thing backward, it doesn't. Oh, this is also calibration. This button here, the plus.
Okay.
Right?
Okay.
Okay. So if you put it here, just put it like that.
Okay.
Okay.
Thanks.
It should be fine. Let me just want to check. Yeah, it's fine.
Thank you.
Okay. Thank you.
So, we you are given this vector space, and as you have told me, you have given a subset. Right? Remember, this vector space itself comes with its own addition. This comes with its own addition. It comes with its own addition. Its own scalar multiplication. It has its own zero vector. And it has its negative vector. Okay? So when you gave me this vector space, you not only gave me the set V, but you gave me all of this. It already came. And you have given me this subset. Our wish is that S is such a subset that S is such a subset such that on its own it is a vector space. That is our wish. So see, I don't have any other information, right? So I should be starting to find the zero vector here, zero obviously because it's a space. What should be the zero? Well, ab initio I have only the zero over here. Okay? So I stipulate that this zero is actually here. The zero of the whole space is actually in S. Okay? So I stipulate zero is in S. I take two things from here. I need to have an addition. Well, obviously I know how to add them in V. Okay? So it's very natural to expect that x plus y, that addition in V, is actually sitting in S. Right? So, okay? And if I take a scalar lambda and any member from S, by the same way, by the same token, this must be here. Right? Now let's see, the moment we assume these three properties of S, it immediately follows that if X is a member of S, then minus X is a member of S also. Why? Why does this follow? Yes, why? I'm saying if I assume these three properties, then this one follows. I don't need to think about this anymore. Why? Look into these two properties.
I think because of the zero vector.
What does this say? What What is minus 1 times x? Minus 1 times x is nothing else but minus x. Right? So it says for any scalar, if you take x from s, lambda times x is already there, so in particular minus x is there. Alright? So you see, if we assume these three properties, then with the addition defined as in V and scalar multiplication defined as in V, S becomes a vector space by itself. Right? So with the addition, so it becomes a vector subspace. And that becomes our exact notion there. Okay? So we define, so here is our definition. A subset of a vector space is a vector subspace or we often say the subspace of V if let's see if I still need this. Let me see if I still need this. If I say this, okay? Let me see if I still need this, okay? Obviously, as you said, from here, taking lambda equals minus 1, it follows that the negative vector is also there. Right? Taking lambda equals to 0, it tells me 0 times x, which is 0, is there. But there's a crux. See, this is an implication statement. So implication statements are a little bit difficult, right? They are not just saying this happens. It says if this happens, then this happens, right? So it says if, so there are two conditions, this and this, right? I'm saying, let me see, I'm trying to say that I need this. Why? The first statement is actually an implication statement. It says if xy belongs to S and lambda is a scalar, then x plus y and lambda x belongs to. I just throw away the second condition. Suppose if I take S to be empty subset. But then the hypothesis part is vacuously true. Right? There's nothing in S. Okay? So this is vacuously true. Therefore, the implication statement is always true. So for taking the empty subset, the first condition is always satisfied. But the empty set can never be a vector space. We know that the smallest vector space has one element, 0. Right? So the empty set shouldn't be considered to be a vector space. So there must be a way to stop it. And that's that second condition. 0 belongs to S. Okay? You either say that you are taking any subset, then it should satisfy these two, or let's see, suppose you tell me that the subset is non-empty. If the subset is non-empty, then I can take an X from there, right? And then taking lambda to be 0, 0 times that X which is there I have taken is 0, so 0 also belongs to S. Right? So this statement, the only effect of this statement is to ensure, so this part, the role of this in this definition is to ensure is not a okay? So that is very vital. So this part is very vital. Okay? It's just to ensure that the subset is not empty. If you start off with a non-empty subset, then just stating this first condition is enough. Okay? But the non-emptiness is something which has to be ensured. Okay? Clear? So this is the definition of a vector subspace. Alright? So now, once we have, so is this definition clear now? All centers? Now, we have many more. So with this, we have many more examples now. So, each line through the origin. So, M times X. Now, I should write it this way. So let me say LM M is not equal to 0 and this is equal to so I'm giving you so LM for each n I'm defining a subset, right? So LM is a subset of okay? Each one of them, or so if you want to draw a picture, it looks like this. Okay, and this line is a 0, the y-axis. Okay, so what is M? M is actually the slope. Okay, M is actually the slope. So these are nothing else but lines to the origin. Okay, these are all subspaces. Okay? These are all subspaces over. All right? So let's see. Okay? Do you recognize what is this? What is PABC? No. Thinking about P, don't think about polynomial. PABC, this is the set of all triplets. So this is a subset of R3. So what is this subset? Do you know this? Subset? This is the equation of a plane, right? Through the origin. Okay. So this is the plane. Okay? So for each ABC, A, B, C are called the direction cosines and so on, if you saw in coordinate geometry, right? Right? So with the positive x-axis, the angle that this plane makes is cos inverse and so on. Okay? So remember the direction cosines and so on for a plane. So this is the equation of a plane in 3 dimension, right? So these are also subspaces, as you can see now. Yeah? So these are all subspaces. These are not all. There are many others. Okay? There are many others which are also subspaces of R3. We'll see them. Okay? So, you see now examples are coming up of vector spaces. Okay? Oh, I'm sorry, R3. Yeah? Those are spaces of R3. Okay? There are many other examples. So, in the self-assessment questions, there are also several examples. Remember the technique which I was saying. So, remember this problem. Things, right? Addition was pointwise, scalar multiplication was pointwise. We showed that this is a vector space. And what did we show? We showed that sum of continuous functions is continuous. Scalar multiplication of continuous function is continuous. And the zero function, we also check that the zero function is also continuous. Right? So, what was it? If we take P to be any one of them, so what I was saying is F plus G belongs to P if F and G is in P, lambda F is in P if lambda is in R, F in P, and the zero function is in P, where P can be any one of these, right? That was the whole idea. Sum is closed under sum and closed. Remember, I told the technique was you are given the vector space, somehow put it inside as a subset of a bigger subspace. And there was also a problem which said that suppose if P is a subset of a vector space V and it satisfies these conditions, P is a subset of V containing 0 and closed under additions and scalar multiplications, then P is a vector space, right? So what I was actually referring back was saying that P is a subspace of a vector space, right? So that was the idea behind showing or exhibiting something in the subspace. Alright, so you have to put it, so that was my technique. You are given P and you would have to find somehow a bigger vector space V such that P is a subspace of P. Okay? That was the idea. Although we use this idea again and again, but this is a formalization now. Okay? Alright? Okay. Now, let's have another example. Suppose P is a subspace and remember the inclusion function. Is a linear transformation. Obvious. That's what we did to everything. This should preserve the addition and the scalar multiplication. Well, that was. What is this doing? Well, it is just taking that element and doing nothing to it, just keeping it there. So the addition is actually the addition in P. Right? And the whole notion of a subspace was discovered so that it is closed under addition and scalar multiplication. That means to make this a linear transformation. So it's nothing new. It's just rephrasing the notion of a subspace. Okay? All right. So, we have now come up with the idea of a vector subspace which is in parallel with the notion of a vector subset. Of a subset. Okay? Now, suppose, so let's carry on this analog. 6. Wait. Subsets. Over here we have subspaces. Good. Now, there are a few questions. The smallest subset. And here also we somehow know already from what we have done, the zero, which contains only the zero element, right? That is the smallest subspace. Okay? All right. Then over here, so here X was the set. Here V was the set. So X was the largest subspace. Here V is the largest. Now comes a few other questions over here. Suppose I have A and B are subsets of X. This gives rise to union A union B, A intersection, right? They're subsets. So a similar question can be asked. P, Q are subsets. Now, let me use this symbol. I shall be using this symbol sub of V to denote the set of all vector subspaces of V. Okay? Sub of V is vector set of all subspaces of V. Is a set. Okay? So PQ belongs to subspace. So naturally, my question is, what is P union Q? What is P intersection Q? Okay? Let's see. We'll come back. We'll come back to this page. Okay? So let's see. So P and Q. This is the first thing. Any intersection subspace. So the intersection part is simple. So let's have a quick look into the proof and what does it say. Yeah, that's a problem. Now this one creates problems when you have this proof. So if you give me any collection, this is where I will require the notion of an index. So let's try to look at it firstly quite naively. So this proof will be a little bit longish because I want to introduce this idea of index things. So, first let's take 2. Suppose, although I'll be doing it in 3 steps, okay, but essentially the third step is everything. That's the actual proof. But I've never done indexed subsets or things till now, so that's why. So suppose I take S and T to be member of subspaces. Subspaces of V. So what do I mean by this? I mean to say that if I take 2 things from S, their sum is in S. If I take 2 things from T, their sum is in T. Okay? If I take anything, so similarly for scalar multiplication, right? So now, let me look into this set S intersection. It's a subset. Now 0 belongs to both S and T. Okay? So 0 belongs to this since so immediately we know that this intersection is non-empty. Right? Okay. Now I'll do in one step. Let's see. Let's take X and Y from S intersection T and a lambda from R. Instead of doing those 2 checks, I'll be doing it in one step, right? So what is it? Now, X plus X and Y belongs to S intersection T. This implies that X and Y belongs to S and XY belongs to T. Right? It's the same thing. Okay? That's the intersection. Yes?
The first one, which just subpoint after after you put in that one. Is it instead or is it zero?
Is it?
Is 0 or instead?
0 is the 0 vector. Right?
I just been checking about the
empty set I shall always write as a cancel 0. Okay? So this means that since S is a vector space, a subspace, this means that X plus lambda times Y is in S. Yeah? And so this obviously therefore tells me that X plus lambda times Y is in S intersection.
I got it before that.
Yeah.
Because I would put it so does it make when you actually put it going to the address?
What you do is exactly the same thing, right? Because if you take, you will say X belongs to S and Y belongs to S. Therefore, X plus lambda times Y. Oh, you separately mean X plus Y is in S and lambda times Y. Yeah, that's why I said I condensed the 2 into 1. Right? And in the self-assessment questions, there is a problem saying equivalent formulations for a subspace, in which this one will appear. Yeah. Yes? Okay. So now, if I did take three things, will there be any essential change in the proof? It's the same thing, right? So this, after similar steps, irreducible. Sorry, sub of V. And you can do the same thing for 4, 5, but
So it simply follows the same pattern.
same pattern. Exactly. Correct. So it is the same. And what is the intersection of all of them? Something belongs to intersection even only if it belongs to all of them. That brings us here. Now you saw that in your examples, you saw, where is it? LM. Each LM, so you saw over here, these LMs are all members of sub of R2. And M can be any real number. Right? So it is not that there are 2, 3, 4, 20 billion. There is something also called L pi. Right? The slope is pi. There is also something called L of root 2. Right? So you know from your course in real numbers 1503, there are uncountably many subspaces of R2. Right? Uncounted as very real numbers. Okay? So it's a too big a collection, right? So it's not that about 2, 3, 4. What I'm trying to say is there is so it is indexed for each member in M, there is a subspace. Right? Okay, so for each member in reals, there is a subspace. See over here, it's something more. It's something for each triplet ABC in R3, there is a subspace. Okay, so this, for each this in this, it could be very strange sets also, right? So just to say it in one word, we come up with this notion of indexed. We come up with this notion of indexed families. So this is the actual proof, but before I do so, let me give the definition of this index. So, SI for each I, and what is this? This is called the indexing set. It could be very, very different from the vector spaces or whatever that as you saw just now, right? It could be very different. It could be, all right? So what I'm saying is, you give me any set I, and for each member of I, there is a subspace. Okay? Clear? Got the idea from those examples? Yes.
You can also say that if every member in I is a subset, there's all the properties are satisfied, like the zero vector, the addition, and the scalar multiplication.
For SI, not for I. Not for small I or capital I. Because capital I is, I don't know what is it. It is just a set. Okay? So for over here, your indexing set was reals, right? Here your indexing set was R3. Okay? So you see, it can be very, very different, right? So that's why I am saying that for each set, you have something like this. Okay? Now, how do you define this intersection? just as we defined. So how do I define this set? We write it in this way. We read it as intersection of SIs as I vary over all the indexes in I. Right? So what is this? X is a member of this if and only if for each I X is a member of SI. Right? You have three members, three elements. That means your indexing set was actually. So finite things we don't bother when you take two sets, S and T set. Your indexing set has two elements, 1 and 2. One goes to S, two goes to T. Okay? What was your definition of intersection? X belongs to intersection if and only if it belongs to each one of those sets. Okay? See, the problem with finite is distinguishability, right? We can say this is this, and so on. And this is not same as this. But the problem with non-finite or non-countable things is it's no more distinguishable, right? It is just there, just for each item. Okay? So that's the little bit of a wary feature, but much of this intersection moves over. Okay? And as I said in that exercise, in the first one, what is the union? X belongs to union of I in SI. So that set is defined as, so union means that exists something, right? Some of these must, it's a collection, it's a join of all the backs. So here it means also there exists I in I such that X belongs to SI. Okay? Right? So, now having said so, you can proceed to that exercise on index families, which I said in the first. I skipped that, but now I'll be required in this now. Okay? So now let's see. So over here, since each SI is a subspace, it follows okay? Same argument. Okay? Similar. It will be in the intersection. What is in the intersection? Something is in the intersection if it belongs to every one of them. But 0, the 0 vector in this case, is in every one of these SIs. So therefore it's there. Now let's for each I taken from S. That means for it belongs to every SI. So this means so for each I, x plus lambda y is an SI. Right? Hence, that proves this. In fact, this is the proof. A and B is just not was there to explain. This is the actual proof. Okay? Okay? A and B was just to explain the idea. Clear? So, what's the parallel? Using index sets, why this?